Our next speaker, Gavin Schmidt, is a climatologist and climate modeler from NASA Goddard Institute for Space Studies at Columbia University. And his work uses models that are large-scale atmosphere ocean systems that test climate variability, future climate variability under a warmer world, as well as the character of ancient climates. In 2004, Scientific American magazine awarded him the top 50 scientists of the year. It's a prestigious award. I don't think it came with any cash. Did it come with any cash?
No, and they've cancelled it subsequently.
Yeah, so if it doesn't come with any cash, you know, it's very nice, but
it was a one-off.
Yeah. Anyway, his morning talk is, can we constrain future hydrologic changes by looking to the past?
Well, thank you very much. I like asking. Continue. I can close that. Apparently. Okay, we're back. I'm going to give you a talk that has a question at the end, and that's generally the sign that we haven't actually finished this work, and so we're not actually going to come to any conclusions, and that would be an appropriate conclusion that you can draw right now. One of the things that we do I work for NASA. NASA is not generally very interested in paleoclimate, but it is very interested in hydroclimate. It's very interested in future projections. It's very interested in understanding what's going on right now. And to do that, we build models. But models, when you go out into the future, those are very, very large changes. And we need to find ways to test how credible those models are. And so by looking into the past, that's really one of the ways that we can do that. So is this going to work? Yes. So we're not the first people to think of this, of course. James Hutton was the first person to really express this. And he said, from what has actually been, we have data for concluding with regard to that which is to happen thereafter. Possibly not the pithiest demonstration of this thing. Steven Spielberg did a much better job a couple of centuries later. And this is the real issue. We're going back to look at the future. And then you have to ask yourself, well, why do we need, how do we look at the future, right? We look at the future, and we generally look at the future through models. And there was a very nice quote from Tomlinson at GFDL, and he said, this was in response to a particularly stupid comment on one of his papers. He said, well, if we had observations of the future, we obviously would trust them more than the models. But unfortunately, observations of the future are not available at this time. And so when we're going into the future, we have to rely on models. So the big question when we're looking into the future is, how do we judge the credibility of those models? What is robust that comes out of those models? What is important? And what are the things that are actionable? Right? Models are not good because they're complicated. Models are not good because we've worked on them for 30 years. Models are good because they produce credible predictions that can be validated. If you look at the IPCC report the last time around, and you ask yourself, well, what kind of uncertainties arose from that? There was obviously tons of discussion about uncertainties, but I particularly like this figure. This is a change of rainfall changes in 2100 under one of the mid-range scenarios compared to the present. And it shows what the multi-model average rainfall change was. So they took the 27 odd models and they took all of their different results and they averaged all of those results together. And that's the color scale that you get there. The scale doesn't really matter because the pattern is very similar regardless of what scenario you look at. And there's some very clear patterns here. You have an increase in rainfall right along the equator. We have an increase in precipitation in the high latitudes, both in the southern hemisphere and in the northern hemisphere. And then in the subtropics, you have this drier zone. This is the yellows and oranges, where really we're seeing an expansion of the Hadley circulation and an expansion of the subsiding dry areas. And this looks coherent, and almost all the models have a pattern that looks like this. But when you look in detail and you ask yourself, well, how much do the models disagree amongst themselves? That's where it gets very interesting. And now the black dots here, which you can see, there's a lot of black dots here. There's not very many over here. These black dots are an indication of model agreement, like to what extent this pattern is a robust response to the forcing. So all of this stuff down here in the southern hemisphere, in the southern high latitudes, that's robust, right? All of the models show an increase in precipitation there. The same thing for the changes right on the equator. And there are good physical reasons for this, right? The increase in precipitation in the poles is because water vapor is is converging towards the poles. There's more water vapor in the atmosphere, and it has to go somewhere, and it comes out as rain or snow. Increases in rainfall right on the equator are associated with increases in tropical convection, and that produces local rainfall. But then you look a little bit more closely, and you look at most of the US. You look at the Amazon, you look at the Sahel, you look at India, you look at Australia, and there are no dots. Now, what that means is the models are schizophrenic. It means that maybe half of them, in some cases, are actually showing that it's going to get wetter, and half of them are showing that it's going to get drier. So our ability to make a statement about how robust the model result is there is no ability to make that statement. And so that was how many people live in those areas? That's maybe 1 billion people live in those areas. And we have no idea, well, maybe more, 2 billion people live in those areas. And we have no idea what to tell them from all of our modeling studies about how their hydroclimate is going to change. And that's profoundly disquieting, right? That's bothersome. But these areas are also interesting. Because they're areas that have a rich history of paleoclimate studies and observations of change. For instance, the Sahara, we know that it was much greener during the mid-Holocene 6,000 years ago. We know that in America we've got a great drought record from this network of trees. In Australia we have cave records, and in India we have cave records and all sorts of other things that tell us how rainfall changed or how rainfall patterns changed in the past. And so the question is, can we do a better job than just averaging all the models together, even the ones that seem to produce completely contradictory answers? And I think the answer is yes. So we have been involved in this project called CMIP5, which has been a project that has taken our time and effort for about the last 2 years, 24/7 that entire time. We're not the only group that's been doing these runs. NCAR, GFDL, the Met Office in the UK, the climate modelers in France, Korea, Japan, Germany, roughly 30 plus institutions have been doing these simulations. And these simulations are a whole package of different things. You have the future projections, that's all these RCP things. So the RCP 8.5, which Kerry briefly alluded to, that's a very, very strong forcing. If that ever happens, literally we're toast. RCP 4.5 is a kind of more moderate scenario. RCP 2.x, or sometimes it's called RCP 3. This is a very optimistic scenario that assumes that by the end of the century we are sucking carbon out of the atmosphere at a prodigious rate, so that's not going to happen either. RCP 6 is somewhere in between 8.5 and 4.5. They're all scenarios, they're not predictions of what's going to happen in the future, they're all kind of storylines for what might happen. They span a wide range of carbon dioxide levels, but they don't span a very wide range of things like aerosols or biomass burning or something like that. So they're not a full suite of things that could happen, but they are suggestive. But in this suite of runs, there's also a whole set of paleoclimate runs. And this is the first time that we have ever self-organized in this way, where we've brought in the people who are interested in the future and the people who are interested in the past and made them do all the same sets of experiments with the same models, with the same database, with the same diagnostic and the same formats. So if you're interested in whether anything in the future correlates to anything in the past, up until now, you had a very, very hard job. But right now, your job suddenly got a lot easier. And when things get easier, you can do much more interesting research. So I'm just going to give you a couple of examples of the things that people are doing to demonstrate its worth. But first of all, let me ask the question, like, why do we really care about paleoclimate? I alluded to it before, but the main issue is that future climate change is out of sample, right? We have observations for the last 30 years that are really good, the last 50 years which are okay. Going back a little bit further, you know, it gets much worse very quickly. But the changes that we've seen over those periods are tiny compared to the changes we're projecting for the end of the 21st century, right? So those changes are out of sample compared to anything we can calibrate against. That's why statistical models on their own are not going to be very useful. It turns out that when you try and rank the models based on how well they do against observations that we have for today, whether it's the seasonal cycle, whether it's a response to El Nino, whether it's interannual variability, whether it's storminess or anything, these things are not correlated to what the models say is going to happen in the future. You can have one model that has the most perfect seasonal cycle and another model which has the worst seasonal cycle compared to the observations, and they'll both produce the same change going forward into the future. And so getting the seasonal cycle right doesn't tell you whether your model is going to give you the right answer in the future. Paleoclimate, and particularly the paleoclimates we're looking at here, is not an analog for what's going to happen in the future. What we're going to has never happened before in the history of the planet, right? But a lot of the changes that happened in the past are changes that exercise the same machinery, the same processes that we're pushing in various directions in the future were pushed in slightly different directions with slightly different combinations in the past. And so if you think about like taking a car out for a test drive, going around the block before you head off on a cross-country trip, that's the kind of thing that we're looking at. And, you know, I mentioned that, you know, you need to have these coordinated comparisons, and that requires a lot of work, and it's taken us a number of decades to get that far. It needs coordinated databases for the paleo data. It needs improvements in the archives, which we've now kind of got to, and we need to connect the paleo to the kind of future projections, and that's what we've done in CMIP 5, like I said, for the first time since we've been doing this. So with paleo simulations, you can do three kinds of things, right? And most people only think about the first, so I'll just kind of skip through that really. If you do a climate simulation of the LGM, the most interesting thing for most people is to say, oh, well, can you explain what happened at the last glacial maximum? You know, what happened here? What happened there? What was the size of the ice sheets? How did that affect this? And there's lots of people in the paleoclimate community who think that that's why we should be doing paleo simulations. Okay, I work for NASA, and let me tell you, this does not fly in any proposal meeting that you're with where you have somebody from NASA who's paying for the bill. Nobody cares at NASA why the last glacial maximum looked the way it did, right? So all of these different studies, most of what goes into paleoceanography, most of what goes into climate of the past is completely not of interest to most funders in the US. But there's two other things that you can do which are far more interesting. One is to find metrics that cohere between the past and the present. So what you're doing is you're trying to find things that, okay, well, in the past there was this relationship between these variables, and in the future the model suggests that that relationship is the same, and we have, for the past, some evidence that that relationship is actually being credibly modeled, right? And then that gives you a way of kind of projecting that credibility into the future. The third thing that you can do is what I alluded to before, is to differentiate between models, to differentiate between models that appear to have skill when you're looking at the mid-Holocene or you're looking at the last millennium, and hopefully showing that that skill projects onto a different future prediction. And that way, if you have models which are more skillful or less skillful, but they give you a different answer in the future, you might then weight your prediction for the future towards the models that have more skill in the past. And I'll give you examples of both of those last two things. But here's just a sense of what kind of things you have. This is 6 different models that have done a whole suite of experiments. So these top 2 rows are for globally warming experiments, an abrupt rise in full-time CO2, 1% increase in CO2. They're kind of cleaner comparisons than the RCP experiments, but they give you pretty much the same answer. This is for temperature, of course. This is the seasonality, the change between the warm and the cold seasons, and then this is the mean annual temperature, the maximum temperature in the cold month, maximum temperature in the warm month. And then these 5 rows here, this is the 20th century runs. This is the mid-Holocene, 6,000 years ago, and this is the last glacial maximum. And if you don't look at anything else on this little graph, look at this. If you look at the seasonality change associated with a warming world, and you look at the seasonality change associated with a cooling world, there's a kind of mirror image going on there, right? There are connections between how the models respond to cold as they respond to warm. It's not linear, it's not simple, and it's not universal, but there are connections. If you compare those multi-model ensembles to the actual data, this is the historical changes, and then this is the model estimate of the historical changes. I should have cut all this stuff out actually. You look at the mid-Holocene, you can see that there's a lot more. Actually, this is true in all of the data seeds. There's a lot more heterogeneity in the data than there is in the model means. That you expect because you're averaging over a lot of variability within the models, but there's also a lot of noise in the data, right? Data from Paleoclimate is not as good as data from satellites and weather stations today. But you can see that we've got quite a lot of data for the mid-Holocene. We have quite a lot of data for the LGM. And you can't really see how well this works out spatially because this is all kind of washed out because everything is in the -5 to -10 category. But we do have enough data to start to constrain the spatial patterns. So let's look for some robust metrics. Let's look for things which are which look the same in the past and the same in the future. Okay, so here's an example. This is the temperature gradient from north to south, and then this is the shift in the ITCZ, right? And this is a whole bunch of different models, both in future experiments and in past experiments. And what it shows is that there's a relationship, right? It says that the ITCZ will move as a function of changes in the temperature gradient in ways that are actually quite predictable, right? That's a good thing, right? Because we can then say, okay, well, if we know what the sea surface temperature changes are going to be, we can say what the ITCZ, how that's going to move. And that obviously is very important for hydroclimate. Here are some other examples, right? The land-ocean contrast in temperature, right? Here are all the different models for 3 different periods, the historical, mid-Holocene, and the LGM. These are the LGM ones here. This is the mid-Holocene and the historical. And you can see that the land-ocean contrast, and the observations are these big crosses in the middle. And you can see some observations there as well. And you can see that when you put all the models together, there are relationships between the land-ocean contrast that are the same and credible in the LGM as they are in the future and in the present. The same thing is true for polar amplification, and the same thing is true for seasonality, though slightly less clearly. Right? So there are things that you can look at, property plots that you can look at in the models that can be credibly tested in the paleoclimate data, but also are constant through all of the different model simulations. Here's another example. This is the temperature change between the North Atlantic and Europe. And again, here are the future runs. Here are the past runs. This is the estimate from paleo data, reconstructions themselves. And you can see that the models, they don't match everything perfectly, but the relationship between the North Atlantic and European temperatures is quite clearly the same relationship that we see in the reconstructions, right? So we have something that the models do get correct, even if they don't get the same amplitude as we're inferring from the data. So this raises a question when you're kind of trying to differentiate the models, right? All of that stuff that I just showed you was where all the models look the same. But we don't just want all the models to look the same, because we saw on the first rainfall map that lots of models differ in very important regions all the time. So how do you differentiate between the models? Okay, so what you need is some measure of skill, and it doesn't matter what it is. It can be in frequency space, it can be regional, it can be global, it can be whatever variable you like, where you have some data. And then what you're looking for is a correlation of that skill with some future change. So quite often you see this kind of pattern where you have lots of different measures of skill from the different models, but it actually doesn't correlate to the future, right? So this skill, oh, that was good, not good, okay, ooh, better. 4 buttons on here, quite frankly, that's too many. What you're looking for is a skill measure that correlates to this, because right here what you're finding is that whatever future change these models are predicting, it's not correlated to this skill measure, and so this skill measure is orthogonal to the reasons why it's giving the future change that it is, right? It becomes not useful. What you're looking for is something like this, where you have a correlation or a structure to the future change skill relationship that you can use, because now you can say, well, let's imagine that this is higher skill, then this might be more likely to be the future's change, right? Now, the weird thing is that almost everybody works as if all metrics look like this, but the number of people who actually test that this is actually the situation that you have is very, very small. And so if you ever do anything like this, please check that your skill metric actually does correlate to the future change rather than just assuming it. So here's an example that we talked about in a recent paper that's currently under open review. So if you have anything to say about what I'm about to say, you can write an angry comment that everybody can read. What we're looking at here is what's going on in South America, right? That was one of those areas where there weren't very many dots. And the reason why there aren't very many dots is that the models kind of fall into 2 groups. In fact, they fall into 3 groups, but there's 2 which are really quite clear. If you look at the first group, and this is these are the future predictions compared to the present. You see that there's one group that says we're going to have a lot more. This is a lot drier here, and this is a lot wetter, right? So we have this kind of dipole across the top of North America. And there's another group which says, no, that's not going to happen at all. It's going to be wetter there and drier here. And this is a very different pattern. And they're related to one group of models just shifts the ITCZ, and another group of model really expands the ITCZ. And there's different processes that are going on and different balances that are happening there. If you look at what those same models did for the mid-Holocene, what you find is that the models that have this kind of dipole structure for the future also have this same dipole structure for the mid-Holocene. And the models that had just a shift in the ITCZ also had something that looked similar to that in the mid-Holocene. And if you correlate that and you say, okay, well, what's the relationship between that change in the dipole in the mid-Holocene and the change in the dipole in the future, you do see this relationship, right? So what we have here is the possibility of looking at the data and saying, okay, well, which group of these models is more realistic? What actually happened in the mid-Holocene? Can we say that it's more like these models or it's more like these models? And it turns out that there's a data synthesis that's in press, I think, that suggests that the group 1 models are more realistic. So that would be these two up here, which if we go back, that's this kind of pattern here. So that would be suggestive that you're going to expect drier conditions northern South America and then wetter conditions in the Nordeste region. Okay. So I think these are the kinds of things that we should be doing, and we should be doing much more often. One of the things that we've worked on, particularly at GIS, is including more proxies of what's actually being measured in the past. One of the key measurements that you use are water isotopes in carbonates. These are records from cave records from Borneo, Sulawesi, and Flores in the Western Pacific warm pool, and you can see that there's been this large shift. This is the early Holocene here, moving to the present. This has been a large shift, kind of like from about 10,000 to about 5,000 BP in all of those places. And when you put that into the model and you ask, okay, what have the isotopes in rainfall changed like? What you get is a big shift of around 1 to 2 p per mil, which actually matches these data really well. So when it turns out that the water isotope change is very related to how water is shifting, right? Where water is coming from. So if you're getting more tropical source water, or you're getting more water from the East or West Pacific, these have signatures in the isotopes which are directly tied to the hydrological cycle. If not, they're not directly tied to local precipitation, but they are tied to large-scale changes in the hydrological cycle of the tropics. Some metrics are not robust. We can look at things and we can say, okay, we've got a great correlation in the past, but the correlation in the future breaks down. Now, one of those is the PDSI, right, the Palmer Drought Severity Index. Because of the large temperature component in the standard version of that index, you can have models show a really nice correlation between this is soil moisture, and then this is the PDSI. This is over North America. They show a very strong correlation, which you can't really see because it's kind of obscure. But anyway, the correlation is quite strong in the historical and past millennium runs, but it breaks down completely when you go into the future records.
Yeah,
right?
What's PDSI?
Palmer Drought Severity Index. It's an index which is based on a model of how evaporation works, which is not terribly accurate. And the idea is that when you have a very negative PDSI, then you're in drought conditions, and you have a very positive PDSI, you're in wet, kind of fluvial conditions. And there are records of PDSI that have been derived from tree rings from a whole network across the North America, for instance. So there's the NADA the NADA PDSI that's here. So you can't really quite see, but there's the ups and downs are about the same size as the models predict, but they're not coherent, right? One of the things that we've just started to see is that the models will produce kind of mega droughts in North America at about the right frequency, but they're kind of uncorrelated to any forcing. It's one of those random things that's happening. So there's some very interesting stuff here. But if you take it forward, if you say, okay, well, my PDSI is going to change dramatically in the future, that doesn't necessarily mean that your soil moisture is going to disappear and that you're going to be in some huge drought condition. And these are two models where you can see this really strong divergence between the soil moisture and the PDSI in the future in completely opposite directions, right? So here, this model is saying a wetter North America. This model is saying kind of about the same in North America, but the PDSI indices would indicate that North America was in some absolutely unprecedented drought situation. So you've got to be a little bit careful. So let me conclude. I think it's quite important for people to realize that the multi-model ensemble actually does a pretty good job at simulating the key periods that we've looked at for the paleoclimate. That's the mid-Holocene 6,000 years ago, the last glacial maximum 20,000 years ago, and the last 1,000 years, so from the medieval period to the present. And it's very important that you realize that these are out-of-sample tests. Nobody in any of the modeling groups twiddled with their models in order to get a better LGM, right? It's for practical reasons, it's impossible for us to do that. There are many climate features and relations between climate features that are robust between the past and the future. That is an absolutely key insight. There are constraints, therefore, on hydroclimate going into the future, which we're just beginning to explore and publish on. And there's going to be a lot more work done on this in the next few years. We can see that there are going to be shifts in ITCZ as a function of SST gradients. That's a robust result. We can distinguish between models, for instance, in the South American case, between models that got that dipole change right in the mid-Holocene and who also predict a dipole-like change in rainfall in the future. And those seem to be more credible than models that don't have that pattern in the past. And so instead of doing the multi-model mean for ensemble, for the Amazon, we can actually say, okay, well, those models over there, we're not going to pay much attention to those. We're going to downweight them. And we have a credible way of doing that. People have been looking at the mega droughts, particularly in North America. They do seem to be modeled in the GCMs. These are things that the models are capable of producing. But as yet, we haven't found any reason to think that they're being driven by any external forcing. They're just one of those internal things. Now, that might not, that conclusion might not be sustained, but right now that seems to be the conclusion that we have. And the key thing is, there's a lot more work to do. If you're people who have not really looked at GCM data before, or you thought that it was too complicated, or you thought that it wasn't going to ask the question, it wasn't going to be able to answer the questions that you have, think again. The CMIP5 archive is an absolute treasure trove. It's roughly 3 petabytes of data. It's the 3rd largest distributed archive of information in the world after CERN and Google. It is an enormous resource, and the number of people who are looking at it and the number of things that could be done with it are vastly out of proportion. And so if you're looking for a good project for a student, if you're looking for an interesting thing, you thought, oh, what about this? Look at this archive. And I can't promise that it's perfect, but it's a huge resource that deserves to be looked at far more closely. So I'll just leave you with a parting thought. Prediction is difficult, and actually not just at the future, but also at the past. And the task that we've been appointed to do is a real challenge, but nobody said it was going to be easy. But we can still do better than we're doing. Some of you might remember a really terrible model, a terrible movie called The Day After Tomorrow. There's a scene where they're all in the climate model control room, and somebody comes in and says, "Grid models can't save us now." And actually, that's the only line in the movie that was actually true. So. And anyway, so that's about it. I got books. I tweet. This is new tweeting. Anyway, so that's fun. Thank you very much.